Good. Thank you, Suzanne. So, pleasure to be here today to talk about CO2-Plume Geothermal and how it enables CCS. So you can see a lot of names here on the slides. We're all actively working on that in the GED group at the ETH in Zurich, including my colleague Tsubasa. Good. CO2-Plume Geothermal, what is it? So this was co-invented by Professor Martin Saar, actually back in 2011, and it's all about using the benefits of CO2 as a working fluid to turn CCS into true CCUS. And by that, I really mean the utilization as well as 100% of the storage of the CO2, all in the same project. And that's something you don't see happening a lot. So what does it look like? On the right-hand side, you can see it starts off with just your regular CCS project. So you've got a CO2 source, could be capture plants, could be pipeline. Then that CO2 is injected in a subsurface reservoir. But if it's highly transmissive and it's hot enough, you can then turn it into CPG by producing back the geothermally heated CO2, expand it through a CO2 turbine, then cool and condense it, and then bring it back into the stream coming from the capture plant. So in the process, all of the CO2 is stored, but also power is produced, which is very useful, both to power the operations itself, but if there's any access to bring it to market or the local communities. So curious, how many people have already heard about CPG? Maybe a show of hands. All right, quite a few. Good. So I'll talk a bit about power, but I think the real message that I want to bring across today is not just about the power, but it's also about how the underlying CCS project can benefit from this technology. First, power, and let me then talk about the difference between using CO2 as opposed to water as a working fluid. So here you can see a couple of graphs with on the y-axis the reservoir depth and on the x-axis the transmissivity of the reservoir. So that's the millidarcy meters of the reservoir. And the contour lines that you see here is how much power can be produced from a reservoir with 1 square kilometer of footprint, so a 5-spot. And on the left-hand side, you can see the power that's produced using CO2. And if we just take 1 point as an example indicated by the yellow star, you can see that this square kilometer of surface footprint translates to roughly 3 megawatts of power for CO2. If you then move to the case where you would use the same reservoir but use water as the working fluids, you find you're roughly at half the power that you can produce. And this ratio, so this factor 2 benefits can be plotted. And you can see that on the right-hand side, the plot there is the benefit of CO2 over water. And you can see that that star again lies on that factor 2 improvement. So if you look carefully, you can see that actually on the right-hand side, all the way to the top right, this factor drops below 1. So there water starts becoming more beneficial. But actually, when you think about it, how many reservoirs you know of that are very deep and at the same time have a very high permeability? There's actually quite a few of them. So most of the opportunities that you're looking at will be towards the bottom left-hand corner of that plot there. So the question then is, how is that possible? How can you get more power out with CO2? Certainly you cannot beat the specific heat capacity of water. And the answer is, you're right, you can't. But there are other things you can do. So here you see an equation for the thermal energy flux, and this will be my only equation today. But what you can see here is that indeed you take a 50% hit on the specific heat capacity. But this is more than compensated by the benefits of primarily the viscosity of the supercritical CO2. So the mass flow rates you can get through the reservoir are a lot higher than you can with just water. And that's how in the end you can get more of the energy out. Secondly, as icing on the cake, there's also the thermal siphon effect. So there's a big density difference between the fluids that are cold on the injection site within the well and the hot CO2 coming up on the production well. And that density difference can drive the system almost by itself, and that's called thermosiphon effect that you won't find in water-based geothermal operations. Good. So in short, this was the power component, but let me get to the second part, which is how the underlying CCS project can benefit. So here you see a plot with on the y-axis the pressure of CO2 and on the x-axis the temperature of CO2. So it's just a PPT diagram of CO2. And actually the conclusion you can draw from this is that taking the heat out of the surface, you're actually doing the subsurface a service in itself. Because by cooling the CO2, you either make it more dense, so you can increase the storage capacity of the reservoir itself, or it means that you can reduce the pressures, and the pressures are, of course, a big concern in the CCS operations. So you can just plot a particular example here. So by cooling the temperature, you can see that each degree in temperature roughly translates to 1% of improvement of your CO2 storage or your pressure. And that's just one component of how your storage capacity could increase. The other one is volumetric sweep. So CCS projects are typically characterized by having very limited control over your CO2 plume. You inject and then physics takes care of the rest. And you won't have optimal sweep in your subsurface reservoir. So the moment that you start applying CPG, you actually have a bit more control over your local pressure gradients and where your CO2 then migrates to. And especially looking in the US where you want to stay within your area of research, this can be quite a benefit as well. And potentially in the process also arrive at a higher volumetric sweep and therefore higher capacity. Moving on to the economics. First of all, CapEx. CCS projects really need to inject everything that they have in their agreements. So typically you'll find a lot of redundancy built in to the injection capacity. And it's a real benefit if you have the optionality to change flexibly your producers to injectors. So if there's an operational, if you find some surprises, which you often do, then having these additional producers can help to sustain the plateau. And additionally, also towards the end of economic life of your geothermal operation, so say after 30, 40 years when your cold front finally does arrive at your producer wells, you can then convert these producer wells back into injectors. And by then, pressure might be a bit higher in your storage reservoir, and having this additional injection capacity can help to sustain the capacity for a few more years. And in the end, you're being paid for the capacity. You're less being paid for the declining injection in your site. So this is how CPG can help with that. Finally, there's a lot of information that can be gathered from the producer wells. So there's a lot of MMV that comes almost for free with the CPG operations. Operations. So in Aquastor, there was a big issue with intermittent injection of CO2, specifically the halide scaling that could occur there. Now, again, you have more optionality in CPG because you have two CO2 streams. You have the CO2 streams coming from your capture plants. But if your capture plant is down, you still have a CO2 stream coming from the producer wells. So that maintains the uptime of your injectors and potentially can help with mitigating some of these concerns with intermittent CO2 injections. Finally, but not lastly, there's also the component of public acceptance. So this is CO2 disposal with benefits and can really help to bring in the local communities to show that CO2 is not just waste disposal, it's really more than that. And a topic that I think is not getting enough attention as well is the CO2 intensity of CCS projects themselves. So by being able to leverage the CO2 to locally produce clean power to power the operations can also help in that respect to get the public acceptance there. Good. Then moving on to some of the challenges. So what we still need for large-scale adoption of this technology is we need more work to be done on the development of lower temperature CO2 turbines. There's quite a lot of work ongoing in higher temperature turbines, but we need a lower temperature range. Also, on the cooling and condensing side, high pressure cooling and condensing using with CO2. Equally, on the production side, there's work needed on the treatment of the production stream, for instance, to take out the water. And there's actually quite a number of groups that are working on treatment facilities for that. Equally, as is always the case, technology is moving faster than regulation. So we need the the regulatory support to make this technology able to fly, because we need to be treated just like any CCS project. Because in the end, we still store the CO2 just like the underlying CCS project does. So we're working actively on these challenges. For that, we've set up a CPG consortium. That's what we did last year together with Shell, with Petrobras, Holcim, Altair Energy, of course the ETH, and several academic partners that are also in the room today. And the objective of this consortium is to demonstrate the potential and technical feasibility of CPG to enable FIDs on commercial scale projects. And so we're currently working towards a first field demonstration in phase 2 of the consortium, which is starting next year. So here's also the website. It also includes links to the over 16 peer-reviewed publications that we've published to date. So to wrap up, CPG is an emerging technology that has the potential not just to produce power, but also to benefit the underlying CCS projects. And I'm very keen to learn more about overlaps you see with your area of research or your ongoing projects. So thank you very much for your attention.